Okay, hello, this is Brian Washburn, and this talk is going to be about air resistance and projectile motion. Okay, so in the past, you have looked at projectile motion and free fall without any air resistance. And if you looked at that type of problem, you had an object of mass m, and the only force acting on it was the force of gravity downward. Now what we like to do is include a second force, that of air resistance. And what we want to do is we want to come up with a physical model for the magnitude and direction of the force of air resistance. So if we think about air resistance, we want to come up, so we're going to use, your book uses the symbol little f, and we want to come up with some functional form for that air resistance force. So we can use our experience to come up with kind of ideas for the magnitude and direction. So the magnitude, think about the magnitude. If you ever ride a bicycle, you notice that if you're stationary, you don't feel any resistance due to the air on you. But once you start moving, you feel a force of air resist you, and the faster you move, the stronger that force is. So we can say the magnitude of that force depends on our speed, how fast we're going. So we can say that the magnitude depends on the speed v. The direction of the force, well, the air resistance, once I notice that the force, or that frictional force, always causes me to slow down. And so in terms of direction, the direction is going to always oppose the direction I'm going. Okay? And so if you think about it, you go back to this picture I have here, if I have a speed like that, and so this is, sorry about that. So I have some speed here. The direction of my, the direction is going to be of the force is going to be oppose that, and the magnitude of that is going to be how fast I go. Okay. So we can write a more sophisticated form. We can say that F of the frictional force is going to be equal to F of V in the opposite V hat direction. V hat is a unit vector along the direction of this velocity. You can write it like that. Okay. Now we can also write this as in Cartesian. Now again, we're working with a Cartesian coordinate system, so that's that. We could write this as Vx x hat plus Vy y hat divided by the magnitude Vx squared Vy squared. Okay. That's what's going on there. Okay. Now we got the direction. Let's talk a little bit more about the magnitude, the F of V. So we can start with simple descriptions. We're going to look at something called linear air resistance, where V, the magnitude, is going to be equal to a constant, B, times the velocity V. And this is going to be called linear air resistance. And the constant B is going to depend on two things. It's going to depend on the medium I'm propagating through, and also the diameter of the object. And the way it works is that linear air resistance affects things. The strength of the linear air resistance, the term B, depends on the medium itself and the diameter of the medium. So we can write that as B is going to be equal to, in the way you're symbol using books, beta, which depends on the medium. So that could be air or water or whatever you're going through, and then the diameter of the object. Okay. Quadratic air resistance obviously depends on, sorry, let's just write this again. quadratic air resistance depends on a constant c p squared. Now, that's going to depend on the medium itself. That constant is called gamma. But it depends on not the diameter, but the diameter squared. It really depends on the area. And the reason why is because quadratic air resistance comes from the fact that the object or the projectile has to accelerate some blob of air or fluid with it. Okay. So then the question asks, okay, well, if I have some object, it could be a oil drop or it could be a baseball, what terms are significant? Is it the linear term? Is it a quadratic term? Or is it even a sum of the two terms? Okay. So to answer that question, what you can do is you can look at the ratio of the quadratic term to the linear term. And if we write this down, we can say this is gamma d squared divided by beta d, or that's going to be equal to gamma divided by beta d. And you can see here that objects that have a larger diameter, the quadratic term is going to dominate. For example, if I have a baseball, your book does these calculations. Just sticking in the numbers, you can see that the ratio of the two is on the order of 600. So that means that the quadratic air resistance is 600 times stronger than the linear. If I have a raindrop or an oil drop, this ratio happens to be on the order of 10 to the minus 7. That means you can totally ignore the quadratic term. It's only linear air resistance. So we're going to first look at linear air resistance, okay? And the reason why we're going to look at linear air resistance is because we can it's an easier problem to solve, okay? And in fact, quadratic air resistance, projectile motion with quadratic air resistance, we cannot solve that using analytic methods, okay? So let's take a look. All right, so we're going to look at linear air resistance, and we're going to start with F equals ma. So we're going to start writing down m. Okay, again, we're going to start with Newton's second law. Okay, of course, we're going to write this in terminology, and this is the net force acting on it. And there's two things. There is gravity downward, and then there is the linear air resistance. Now, instead of writing this equation in terms of r, notice I have a v here. So let's just write this as mv v dot mg bv. Okay, so that's a vectorized equation. Again, what I'm going to do is I'm going to pick two-dimensional motion. We're not going to do three-dimensional motion, x and y. And so let's break up this equation in terms of x hat and y hat components. This is the x hat direction, okay? Sorry. Okay. And what I can say, this is going to be equal to, well, what do we have? We have m, g. Oh, sorry. No g. Actually, there's no, sorry, that's a mistake. There is 0. And then we have b, v in the y hat direction. Okay. Oops, sorry, x hat direction. Let's write that. Get rid of that. Okay. So that's pretty straightforward. And then in the y hat direction, we have mvy. We have minus mg, it's downward, and then minus vy. Okay. And then, we forgot the dots. There's this dot here, and then there's that there. Okay, so notice what we have. Our two equations are going to, let's divide by m. If we divide by m, I get Vx dot is going to be equal to minus b over m Vx, okay? And then Vy dot is going to be equal to minus g minus b over m Vy. Okay. Now the nice thing with that is the equations are, first of all, they're not coupled. The first equation here, call this equation 1, just depends on Vx. So that basically says the rate of change of Vx is equal to a constant times Vx. The second equation only has Vy. So notice that those equations there are uncoupled. Okay. So that's the nice thing. So first of all, if we look at these equations and we're going to solve them, we want to identify a couple things about the differential equations. First of all, they're first order differential equations. Okay, that's the first thing. Second is that they're uncoupled. Okay, meaning that the first equation only has Vx in it. The second equation only has Vy into it. And then how we're going to solve? We're going to solve by just direct integration. We can just integrate those equations. Sorry, thinking ahead. Okay, so that's how we're going to solve those equations there. Okay. Okay, so what I want to do, what we're going to do in class, so what are we going to do in class next? So let's go back. Let's take a look at Vx dot, okay? And so we have equation number 1. It's going to be Vx dot is going to be equal to minus B over M Vx, okay? So in class, we're going to solve for Vx as a function of time, okay? Then once we have Vx as a function of time, then we can integrate again and solve for x as a function of time. Now notice in order to do this, we have to have initial conditions, okay? And the initial condition is going to be Vx naught, okay? And then to get this completely, we have to have an initial condition of x naught, or x at time t equals 0. That's the first thing we're going to do in class. Second thing we're going to do in class is we're going to solve Vy dot, and that's going to be a little more complicated. G minus B over M Vy. Okay. Again, what we're going to do is we're going to solve for Vy as a function of time. We can again directly integrate, and then eventually we're going to solve for y as a function of time. Okay, so that's what we're going to do in class. We'll see you there. Okay, so again, please review this, read the book, review this little introduction before coming to class. All right, we'll see you there. Bye-bye.